Let me make sure the audio is working. Yep. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class, this opportunity we have just to meet and study your creation. Help us to glorify you, what we do, Lord. In my prayer, Lord Jesus. Amen. Let's see here. So, we were in the midst of deriving the rules, and these rules are important because they save you the trouble of finding the full Laurent series of a given function. Now, that said, if you have the Laurent series, there's really no need for the rules, and you can just read the residue straight off the thing, right? So, oh, lest I forget, it is Trump Tuesday. So let's see here. There we go. So far, only positive comments. I checked, but what's that?
I said most math people are logical.
Most math people are logical. Yeah. I found the attendance sheet, so let's try to take it out for a spin. All right, so I'm going to add a date. All right, so if, let's say, Z naught is an isolated singularity of f of z, and f of z is equal to a sum n equals minus infinity to infinity of a sub n times z minus z naught to the n, right? So like that is equal to, you know, a sub minus 2 over z minus z naught squared plus a sub minus 1 over z minus z naught plus a sub 0 plus a sub 1 times z minus z naught, etc., right? Then the residue of f of z at z naught is simply equal to a sub minus 1. All right? So that's the definition of residue. We should keep that in mind as we calculate things, right? So last time we had rule 1. Rule 1 says that if f of z has simple pole at z naught, then the residue of f of z is z naught is given by the limit as z goes to z naught of z minus z naught times f of z. All right. Rule number 2. All right. If, I'll do this one in blue. Blue, 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 blue. If f of z has a double pole, at z naught, then the residue of f of z at z naught can be calculated by the limit as z goes to z naught of the derivative with respect to z of z minus z naught squared times f of z. This perhaps may be reminiscent of the formulas we saw in the partial fractions discussion earlier in the book, right? You remember those? I think this is the same mathematics, really. But I haven't made the connection explicit in these notes, of course. So how would we prove this rule number 2? So like we have f of z is equal to, how's it go? Let's see here. We'll say a sub minus 2 over z minus z naught squared, right? Plus a sub minus 1 over z minus z naught. And then plus higher order stuff, right? What happens when we multiply this by z minus z naught squared? We get a sub minus 2, right? Plus a sub minus 1 times z minus z naught, right? Plus a sub naught times z minus z naught squared. Plus a sub 1 times z minus z naught cubed, right? And then what happens when we differentiate that? We get what? We get a sub minus 1, right? Plus 2 a sub naught z minus z naught plus 3 a sub 1 times z minus z naught squared, and so forth. So what happens if we take the limit? I mean, so this implies the rule immediately, right? If we take the limit of this, we get to here, right? On the flip side, what is, this is also equal to what? A sub minus 1, right? Which is exactly what we need to happen. That is the residue of the Laurent series. Yeah?
When we multiplied by z minus z naught squared, was that to get rid of the singularities within the first two terms?
Pretty much. It allows us to isolate. It allows us to isolate the coefficient of the reciprocal term. That's what we're after. So, but that's rule number 2. For a double pole, multiply by z minus the pole, z minus the singular point squared. Take the derivative of that, and then let the limit as z approaches. So the limit as z approaches z naught, like pretty much this is just here as that is helpful because it means what? It means that you're looking at z close to z naught but not equal to z naught, right? So it makes this expression reasonable. But in practice, that limit is always kind of dumb. At least in my experience, these limits are really just evaluations in most instances, in most examples, all right? So, all right. Let's look at rule number 3. Actually, I'm going to skip rule number 3 and go to the triple pole rule. This doesn't have a name, but let's call it, let's just call it triple pole. So this is not in my notes, but I think it's worth us taking a little detour. I think it is in the textbook. I'll look it up when I get a second. Tell you where it is. Because every so often, you want to calculate the residue of something that has, like a higher order pole. So a triple pole, we'll just calculate this, right? That means f of z is like a sub minus 3, z minus z naught cubed, right? A sub minus 2, z minus z naught squared, plus a sub minus 1, z minus z naught, right? Plus a sub 0, plus dot, 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 right? Our goal is to describe some calculational procedure to isolate the a sub minus 1, right? So on the basis of analogy with what just worked, I suggest we multiply not by z minus z naught squared, but this time z minus z naught cubed, right? So we have f of z, z minus z naught cubed is equal to a sub minus 3 plus a sub minus 2, z minus z naught plus a sub minus 1 z minus z naught squared plus a sub 0 times z minus z naught cubed, right? If we differentiate once, that's helpful, but it still doesn't isolate the a sub minus 1, right? So instead of differentiating once, let's differentiate 2 times. All right, I'm going to do 2 steps at once. I hope that's okay with you guys. So I'm just going to take d squared dz squared to get from here to here. And so on this side, I have, well, I'm just going to write it out symbolically, d dz squared of f of z times z minus z naught. Sometimes I get sucked into the trap of like doing the product rule over here, but that's not the point. Like that, okay, great. And on the right-hand side, 0, 0, and over here, 2a sub minus 1. That one becomes 3 times 2 is 6, a sub naught, z minus z naught, plus dot, 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 all right? So what is this? What is the triple pole rule? Can you see it? The residue of f of z at z naught being a triple pole, apparently, is going to be 1/2, right? Limit z goes to z naught of what? The second derivative of z minus z naught to the 3rd power times f of z. Let me look in this.
Doesn't a sub -2, like, oh, when they're taking the second derivative?
Mm-hmm. And here, I'll tell you what happens in general. So this is theorem 1 on page 310 of Staff and Snyder. All right. And there we find for a pole of order m at z naught, the residue of f, and I'm supposed to be putting semicolons between f and the z naught, but oh well, you can forgive me. Some books put semicolons, some books put colons, some books put commas, whatever. Limit z goes to z naught, all right? And you guys tell me, what should I put there?
1 over n minus 1 factorial, limit of z naught goes to z naught,
Mm-hmm.
dn
The what derivative?
d n minus 1.
M minus 1, yeah, the m minus 1th derivative of what?
Z minus z naught.
Uh-huh. Z minus z naught to the m f of z. So there, have I closed my parentheses? Okay. That's it. So that's what happens if we keep going. You can start to see the factorial appearing because it comes from the subsequent, you know, the m minus 1 fold differentiations you have to do to get back to isolate the a to the minus 1 power. All right, so there you go. Now let's continue on. There's 2 more rules that we need to get. Rule 3. And I think this nomenclature of rule 1, 2, 3, 4 is from Churchill's complex variables, if I remember right. Churchill's complex variable book is a very popular book in my generation. Dr. Sprano had complex out of that, for example. It's been around a little while. I think he had the 2nd edition. I think I had the 6th. So holomorphic at z naught, and if G has simple 0, z naught, at z naught, I guess I should say, then the residue of the quotient. So notice this one's not about a function that's given with a pole. This one's about the quotient of two functions. You know, happen to know the denominator has a 0, right? And the, yeah. Well, all we know for the numerator is that it has a, that it's holomorphic at z naught, all right? This is f of z naught divided by g prime of z naught. All right, that's rule number 3. And let me write down rule number 4 while we're at it. Then we'll prove rule number 3. Let's see here. So rule 4. Rule 4 says that if g has a simple 0, at z naught, then the residue of 1 over g of z at z naught is simply equal to 1 over g prime of z naught. All right? So let's see if we can prove this thing. So rule 3, how do we prove this? So f of z is holomorphic, and which means it's analytic at z naught, right? And g of z has a simple 0. So what do we have? We have f of z can be written as like the sum, right? N equals 0 to infinity of a sub n z minus z naught to the power n, right? And g of z has what form? We can write it as, say, z minus z naught times what? I mean, we could write it out explicitly. I'll write it out. I'm not sure this is helpful or not, but I'm going to write it out. Sum n equals 0 to infinity of like b sub n, z minus z naught, right? So sometimes I call that thing like the h of z. We have that h of z naught is what? Not equal to 0, right? H of z naught is also, in my current expansion, equal to b naught for what it's worth, right? So we're trying to understand what the residue of the quotient of f of z by g of z is, so we should look at that. F of z over g of z is equal to well, I mean, I don't know. I can write out these power series. I'm not sure it really does anything much more for the argument. I'll write them out. If I had a better recollection of all the theorems we've already proved, I think there might be kind of a shortcut here that has less writing. But I'm going to write this out. So that right, let's see here.
This might be a stupid question,
Mm-hmm.
but when you say h of z naught is not equal to 0, are you saying that it's equal to b naught, or is it that 0 is also equal to b naught? I'm confused what you mean.
Oh yeah, I'm confused by what I mean too. Let's try this again. So it matters which order you write things, right? Yeah. So this is equal to b naught. That we should all agree.
Yes.
And that is assumed to be not equal to 0. That's what it means for that was simple 0.
Got it.
I regret all this writing. Right? What I should have done, because I don't think this really added anything. What we should have we should just been content to write f of z divided by z minus z naught times h of z, right? That would have been smarter. okay? Man, I feel like you need to know f of z naught is not equal to 0. No? Okay, my proof has two cases. Either f of z naught is equal to 0, or f of z naught is not equal to 0. So, fine. All right. So if we do this, right, then we can rewrite this as like f of z divided by h of z divided by z minus z naught, right? Sorry. So I guess the question I should ask is, how do we prove... Let me just point out, if we can prove that this is a simple pole, right, then I think we're pretty much done in that case, right? When would this be a simple pole? So two cases, simple pole, or f of z naught equals to 0, which means not a simple pole.
Would it be when h of z is not equal to 0? So when it's a simple pole? H of z naught.
Well, we're given that h of z naught is not equal to 0. My real question is, what theorems did we have before? Can you guys remember? What theorems did we have to characterize like a simple pole? I think I left my notes at the office, sadly. And that's in the previous chapter. What? Yeah?
Something like that or not?
Z naught is a pole of order n if and only if 1 over f of z is analytic and z naught has a 0 of order n. Ah, well that's easy enough, right? So we can look at g of z over f of z, right? Which would be z minus z naught times what? H of z over f of z, right?
What theorem was that? 9.29?
Theorem 9.29?
Yeah.
Yeah. So the theorem is that, so we can prove that this has a, so we can analyze the reciprocal of the function to decide whether or not we have a pole, right? We have a theorem that the reciprocal function has a 0 of order n if and only if the original function has a pole of order n, right? So look at the reciprocal, g of z over f of z, which is this, all right? Now, so we need to break into two cases to complete the argument. And the two cases are either f of z naught, so this is f of z naught not equal to 0. Either f of z naught is equal to 0 or it's not equal to 0. So let's suppose this case right now. Let's suppose f of z naught is not equal to 0, right? Then h of z naught divided by f of z naught is what? It's not equal to 0, which tells me what? G of z over f of z has simple 0 at z naught, right? Because we know that the quotient of h of z by f of z is analytic, right? Because they're both analytic at z naught, that's given. And if that is the case, then that implies that f of z over g of z has what? Has simple pole at z naught. And then we can use, we could use like, we could use one of the previous rules, right? Which rule should we use to calculate the residue then? How about we do the limit as z goes to z naught of z minus z naught times f of z over g of z, right? Which is what? Well, it's from right there, f of z over h of z, right? I mean z naught, right? Because we had to take the limit. But what is h of z naught equal to? B naught, but what else is it equal to as it relates to, like, okay, so like this, let me write this out. This is z minus z naught times b0, right? Plus like b1 times z minus z naught squared, right? It's also equal to, well, plus a sub 0 plus a sub 1 times z minus z naught, right? What is the significance of this as it relates to differentiation of the original function? Taylor's theorem tells us that a1 is what?
The nth derivative over x factorial.
Easier than that, because it's the first one. So, but yeah, it's just f prime of z naught, right? So f prime of z naught is equal to the b sub 0 here, right? So I can also say that this is equal to b sub 0. Because if you, yeah. So then this is f of z naught over, wait a minute. Oh, I'm an idiot. Good grief. What have I done? I'm sorry, guys. I mixed together things. Don't let me do that. Hold on. We don't have the, I'm mixing the two functions. Just a second. Let me fix this. This was, so same idea, right? This is g of z. Forget this nonsense over here. That's just nonsense. Scribble it out. So here, just this. G of z is equal to this. What's the significance of b sub 0 then? I mean, this is equal to g of z naught plus g prime of z naught times z minus z naught, right? Plus 1/2 g prime prime of z naught times z minus z naught squared, and so forth and so on, right? This is Taylor's theorem at z naught. So what I'm trying to say is simply that the coefficient of z minus z naught is the derivative of g. So what I was supposed to put down here was just g prime of z naught, all right? So that's the situation when we have f of z naught is not equal to 0. What if f of z naught is equal to 0? What happens then? Then you have, let's see here, f of z over g of z can be written as z minus z naught times some, let me call it, q of z over z minus z naught times some h of z, right? which is equal to Q of Z over H of Z, right? Which is actually itself analytic at Z naught. So like the factor, so I'm using the factor theorem for f of z because we have 0 there, right? It's at least a 0. I don't know for sure that Q of z naught is like non-zero. I'm not saying it's a simple 0 for f of z. I'm saying it's at least a simple 0 for f of z. But these cancel, right? This is what? Assuming z is not equal to z naught, right? So what's that all mean? That means that f of z over g of z is holomorphic at z naught. So what's its residue? It's 0. There is no reciprocal term. It's a power series expansion, right? What kind of singularity are we looking at in this case? What do we call these? I sometimes call them fake singularities. I mean, this is still equal to f of z naught, right? Divided by g prime of z naught. So the rule still works in this case. It's just kind of dumb because f of z naught is 0, right? And g prime of z naught we can divide by. It's non-zero. This would be the case of a removable singularity. So the residue of a function at a removable singularity is 0. Okay. So then, how about rule 4? How would we prove rule 4? It's going to be kind of anticlimactic after the proof of rule 3, but to prove rule 4, what do you do?
Flip it up.
No easier than that. I can fit the proof up here. Let f equal to fill in the blank. Apply rule 3.
Oh, f equals 1.
Yeah. That's it, yeah. So there you go. Them's the rules. So we can use these to calculate all sorts of residues. All right? Let's see here. I'll do a couple of examples of applying these rules, and then we'll look at our first integration technique based on complex analysis. All right, so the examples, let's see here. I'll try to be quick with the examples here. How about we want to calculate the residue of 1 over z cubed plus 1 times z squared at 0. So which rule should we use on that one? You guys, you got to know your enemy first, right? Know thy enemy. Right? This is a good rule for politics and also professors.
Oh, that would be rule 2.
Oh man! So the one I erased.
Yeah, that one.
Figures. Z goes to 0 of d to z of z squared times f of z, right? So rather than actually writing that down, I'm going to write down what happens. I'll write down the thing we differentiate. So the z squareds be canceling, and you'll get 1 over z cubed. When you look at the proof of these things, it's kind of like, it doesn't seem like it should accomplish anything, and yet it really does, right? So we got ourselves a, what, 3z squared over z cubed plus 1 squared. I think I got a minus 2, right? So there's a reciprocal function, then the chain rule, and I lost my limit. Plug in z equal to 0, I'll write it like that. So, well, that's kind of boring. Looks like the residue here is 0.
What happened to z squared? You said z squared times f of z, where did the z squared go?
So this altogether is what I'm calling f, to be clear, okay?
Oh, so it canceled out.
Mm-hmm.
Oh, okay.
Could you also have needed the limit to the derivative?
Well, this time, yes, but usually no. If we took the limit first and then we differentiated, it would always be 0, right? Oh, you want it to always be 0? Well, life would be boring if that was the case. Let's see here. Here's another one. The residue of 1 over z squared minus a squared squared at a. So again, mission critical here is to notice that z squared minus a squared is z plus a times z minus a, right? So let me just write that out. What we're really looking at is the residue of 1 over z plus a squared times z minus a squared, right? So with that, you can identify from that expression, we're looking at a double pole at a. So I take the limit as z goes to a by rule 2 again. I take d dz of what? Of 1 over z plus a squared. So what I've done is I've taken my function I'm calculating the residue of, I've multiplied by the square of the singularity point, right, z minus a squared. That cancels the z minus a squared out. It leaves me with the part which is non-singular. I differentiate it, which gives me, minus 2 over z plus a quantity cubed, I think. And then I've got to take the limit. I keep forgetting to write my limits. Forgive me, hopefully. So that gives me minus 2 over 2a quantity cubed, also known as like minus 1 over 4a cubed, I think. That was my residue right there. Yeah. Example 3. Yeah, go for it.
Would it be?
I'm not sure. Is it with the denominator of when you have the limit of z?
Mm-hmm.
Merging a, would it be z plus
Well, this is to the minus 2 power, so I do minus 2 and then minus 2.
Oh, so right. I'm with you.
Cool. So we'll calculate the residue of this character here at pi. And then example 4, we want to calculate the residue of cosine z over z minus the 3 times e to the z this time at 3. And then finally, my last example of these fun games with the rules. We'll do that one. Okay, so which rule should I use for the top one? I've got sine of pi is 0, right? And it's a simple 0 because cosine of pi is -1. So I just use, I think, just rule 3, right? I just do e to the pi over what's the derivative of sine? It's cosine, so I got cosine pi, which is minus e to the pi. I use rule 3. This one here, what do you think? Again, it's a simple 0, right? So let me just like, to use rule 3 effectively, sometimes you need a little imagination. So look at this. This is really like cosine of z divided by what? Divided by e to the z, right? And that's all divided by z minus 3. So as I think about applying rule 3 to this function, I think of this as my f of z. I think of this as my g of z. And of course, you could go back and just use rule 1 for this just the same, right? So like these rules are not like mutually exclusive or anything. I like rule 3, so I use it a lot, so I just do, and I forgot my at 3, right? So I've got myself a cosine of 3 over e to the 3 times the derivative, g prime of 3 is what? G prime of z is what? What's the derivative of z minus 3? Just 1. So there you go. Right? And then finally this one, we'll use rule 4 finally. Use rule 4, we get 1 over 2z, evaluated z equals to I, which gives us 1 over 2i, or if you like, minus I over 2. Rule 4. Yeah, that was rule 3.
But it would be just as simple to use rule 1.
Yeah, I think so. You can multiply by z minus 3, take the limit. As z goes to 3, you still just get evaluation. Yeah. Yeah. All right, so this brings us to section 10.2, which, like I said, is our first integral technique. So let me set up the stage for us here. What's the kind of problem we're going to look at? Well, oh man, well, this is fine. I had my heart set on a different integral problem, but this one's fine. Yeah, just debating where I should start my picture. Yeah, picture. All right, so the interesting thing about complex analysis, among other things, is we're able to use Cauchy's residue theorem to calculate various improper integrals. And so the argument I'm about to show you is a pretty typical argument. This is not the only way to do it, but these are certainly the most sort of like baseline examples of this technique. So here's the idea. We're going to look at a half circle right? Half circle like this. Half of a disk, right? And we're going to go, so basically it's got endpoints of r and minus r, right? And then up here, we've got a counterclockwise half circle, which I'm going to call CR. All right, it's obviously centered at the origin. So the region that we're in here, I'm going to call D. Right, so like the boundary of D is the minus r, and I really should call it D sub r because it has an r dependence. So the boundary of D sub r is minus r to r unioned with CR. Right, that's what we're up against here. And so we can consider some function that has, let's say, isolated singularities inside D. Let's say it's got isolated singularities z1 through zk. I'll draw some pictures. I usually use little x's for like singularities. All right, but these are all inside the domain. All right. Then what is the residue theorem? The residue theorem says that the integral around the boundary of D, and so I'm saying these are singularities. Z sub j is isolated singularity of f of z for j equals 1 to k. All right. Then the integral over the boundary of D of f of z dz by Cauchy's residue theorem is 2 pi I times the sum j equals 1 to a k of the residue of f of z at your z sub j. All right. So we can calculate the integral around such a semicircle like that. But the other thing is that this is actually what? It's actually the integral from, over the line segment minus r to r of f of z dz, right? Plus the integral over the half circle CR of f of z dz, right? And that's equal to, of course, the 2 pi I times the sum of the residues. Okay? Specifically, we can take a look at this and we can be a little bit more explicit, right? Like, what is the parameterization of the line segment minus r to r? What's z equal to there? If I take a point here, what can I write? I could just write z equals to x, right? For minus r less than or equal to x less than or equal to r, right? So this character right here is really just the integral from minus r to r of f of x dx, in fact. And so that's an ordinary kind of integral we might look at in calculus too, right? So you've got that for this piece, and then over here we've got integral of CR f of z dz, right? I'm tired of writing all this. I'm going to call it Pac-Man. All right. So the thing is, check this out. If the modulus of f of z, right, is less than, well, see, that's not quite what we do. Let me say a little bit more specific. If f of z is equal to something like, p of z over q of z, right? That's still not what I want to. I mean, I guess let me stop doing it in general. Let's look at an example at this point. That's pretty much the setup. That's pretty much the setup. Just to give you a preview of where we're going, if our rational function permits it, like we're integrating f of z, a rational function in this discussion. F of z is going to be a rational function. And if you have a rational function where the denominator has a higher degree than the numerator, then we're able to bound it in such a way that we can argue that this integral over here goes to 0 as r goes to infinity, which then leaves you with the integral as r goes to infinity of this thing is simply equal to that. So this gives us a way of but we need to, look at a specific example so we can look at how that other piece drops to 0. All right. So in the interest of doing that, let me do it. Okay. Kind of random. That's an actual picture. Somebody's left their picture of a bald eagle up here for some reason.
Been up there for a few weeks.
Yeah, I mean, I stuck it up. I stuck it there. I mean, I don't know whose it is, but. All right. So let me look at a specific example here. We'll start with something relatively benign. What am I on, example 6? So let's look at f of z equals to, say, 1 over z squared plus 1. All right. So if when we want to study, I'm going to focus on the interesting part, which is CR. Right? I'd like to bound that thing. All right. Oh, thank you, I guess. Yeah, you got it. You got it. You got it. You got it. So you guys tell me, what's the equation of CR?
Instead of x plus y, x squared plus y squared equals r.
And y is greater than or equal to 0, right? But we can be more boring and just say modulus of z equals to r. Okay? Modulus of z equals to r. So the question then is, for modulus of z equals to r, if we look at 1 over the modulus of z squared plus 1, can you guys give me a way to make that, what can we put above that? So we can replace the denominator with the absolute value of the modulus of z squared minus the modulus of 1. So here's something you should know about. If we have the modulus of z plus w, that's less than or equal to mod z plus mod w, right? But we also have another relation, which is if you have something plus something, it's greater than or equal to the absolute value of the difference of the moduli. Right? So, so we can use the latter one there to make the denominator smaller. If we make the denominator smaller, it makes the fraction bigger. Right? So I'm using this idea right here. Right? And notice that this is actually equal to 1 over the absolute value of r squared minus 1. Right? We'd like to get rid of the absolute values. I can rewrite this as straight up equals to 1 over r squared minus 1, provided what? R is what? Greater than 1, yes. So this is a bound of the ML theorem, right? this is less than or equal to m times L, where L is the length of CR, which in this case is equal to, what's the length of CR?
Pi r.
Right. So we got ourselves a pi r divided by r squared minus 1. Well, this is very cool, because now we've got the integral over CR of, dz over z squared plus 1, right, is less than or equal to what? It's less than or equal to pi r over r squared minus 1. So what does this tell us? What's this go to as r goes to infinity? It goes to 0, that's right. So, I mean, if you like, I could rewrite it like this. This is pi over r minus 1 over r, which goes to 0 as r goes to infinity. If you don't like that, you could apply L'Hopital's rule to this thing one time as r goes to infinity. It's type infinity over infinity. All right? So let's go back to the Pac-Man equation. What do we have then? We have, taking the limit, we've got the limit as r goes to infinity of the integral from minus r to r of dx over x squared plus 1 plus the limit, and I'll write it out because I don't mind writing things out. Let's see here, dz over z squared plus 1. And that's equal to 2 pi I times the residues. Now, what are the residues? Like, let me draw a picture here. So we're talking about the half circle, right? And we're assuming the radius is greater than 1. That was important, right? That's important to get my bound. It's also important because that forces the singularity of the function in question to happen within the loop, right? Like, there's one here, and there's one down here, right? Because f of z, 1 over z squared plus 1, has singularities at plus or minus I. So we only have one singularity inside the half circle, right? So we do 2 pi I times the residue of 1 over z squared plus 1 at I. And, oh, we just calculated that. I shouldn't have erased that. But we got 2 pi I times, what was it? Negative I over 2. Cool. So 2's be canceling. What's that? Just pi, yeah. The whole point of the argument above is that this piece goes to a 0. And so what this tells me is that the principal value of the integral from minus infinity to infinity of dx over x squared plus 1 is equal to pi. The reason for principal value is that, technically speaking, you may remember this, you may not, I don't know, from Calc 2, when we define integral from minus infinity to infinity of f of x dx, technically speaking, we've got like the limit as, let's say, a goes to minus infinity of the integral from, say, a to 0 f of x dx, plus the limit as b goes to infinity of the integral from 0 to b of f of x dx. In other words, infinity and minus infinity are approached in a way which is in no way tied together. It turns out that if you link these, right, if you're taking